11th chapter, Dual Nature of Radiation and Matter. To understand this chapter, let us use few equations. First equation, energy of a photon. Energy of a photon, E, is given by h nu, where h is Planck's constant and nu is frequency of radiation. This is only one photon, energy of one photon. Second, in 11th standard waves chapter, we have studied V equal to F lambda, velocity, frequency, wavelength. Now, in place of velocity, let us use C. C stands for speed of light in vacuum, equal to, in place of frequency, F, let us use nu and lambda as it is. So C equal to nu lambda. Therefore, nu equal to C by lambda or lambda equal to C by nu. When we know lambda, to find frequency, use this. If we know frequency, to find wavelength, use this. Okay. This implies that energy of a photon is given by hc by lambda. Energy in terms of frequency, energy in terms of wavelength. Third concept, electron volt. Denoted by small letter E, capital V. Electron volt. This electron volt is a unit of energy. So 1 electron volt equal to 1.6 into 10 to the power of minus 19 joule. Since energies involved in atomic physics and nuclear physics are very small, so it is appropriate to express energy in terms of electron volt. This is SI unit of energy. Joule is SI unit of energy. Electron volt is not SI unit of energy. Okay. This is for the sake of convenience, whereas joule is for all calculations. Fourth, examples of fourth, electron volt to joule, joule to electron volt. Okay. As an example, 2 electron volt energy. 2 electron volt is equal to 2 into 1.6 10 power minus 19. This is magnitude of charge of an electron. 1.6 into 2 is 3.2 10 power minus 19 joule. So this is in joule. If energy is given in electron volt, you have to convert that energy to joule and then calculate to find either wavelength or frequency. Okay. Similarly, 48 10 to the power of minus 19 joule. So some energy is given in terms of joule. To express this in electron volt, divide this by charge of electron, 1.6 10 power minus 19 equal to, this get cancels, 48 by 1.6, 4.8 by 1.6 is 3, 10 times 30 electron volt. Joule to electron volt, divide. Electron volt to joule, multiplied by 1.6 10 power minus 19. Fifth, electromagnetic waves and electromagnetic spectrum. Electromagnetic spectrum. Visible, invisible, shorter wavelength is violet and longer wavelength is red. Wavelength longer than red is infrared. Much longer than IR is microwaves, and after that radio waves. And wavelength shorter than violet, ultraviolet, UV. Much shorter than ultraviolet, X-ray, and then gamma. There is cosmic rays. Let us not use cosmic rays here. Students, you know how to identify electromagnetic radiation using wavelength and frequency. Now let us try to identify electromagnetic spectrum using energy. Okay. Suppose red is considered means wavelength of red is about 800 nanometer. Why it is about 800 nanometer means it could be 750 nanometer, 745 nanometer. There is no clear demarcation to say that till here there exists red. So if red wavelength is about 800 nanometer, then corresponding energy is about 1.5 eV. Let us solve this later. Time being, violet, if wavelength of violet is about 400 nanometer, then corresponding energy is about 3 eV. X-ray, X-ray energy is few thousand electron volt. So kilo electron volt. Similarly, gamma, gamma is millions of electron volt. Million means mega. So it is MeV. Capital M stands for mega, small letter E, capital V. Okay. Small letter K, E, capital V. Now let us find this 1.5 eV for 800 nanometer. So first example, example 1. If wavelength of red is 800 nanometer, 800 nanometer is 8 10 to the power of, there is 10 power 2 here, 10 power minus 9 gives 10 power minus 7 meter. Okay, carefully convert. It is 8 into 10 to the power of minus 7 meter. Then energy of this photon, hc by lambda. H is Planck's constant, 6.6 10 to the power of minus 34 approximate value, 3 10 to the power of 8, this is speed of light in vacuum, by lambda. Lambda is 8 10 power minus 7 equal to 2.475 into 10 to the power of minus 19 joule. Don't worry about me, I just used calculator. Okay, don't get surprised. So this is energy, energy in joule, but I want this energy in electron volt. Therefore 2.475 10 power minus 19 by magnitude of charge of an electron, 1.6 10 power minus 19, 1.55 10 power 0, which is 1.55 electron volt. So that number is this number, approximately 1.5. Now I'll give few homework. Second example, lambda for violet 400 nanometer. Express energy of this photon in terms of EV. Next, third, lambda is about 1250 angstrom energy. This energy in EV. If you find energy of this energy will be greater than 3 eV. Energy greater than 3 eV means that falls under ultraviolet. So from thousands of eV to 3 eV, this region corresponds to ultraviolet. So this will be ultraviolet. Okay. E4, example 4, lambda equal to 0.02 angstrom. Very short wavelength. This should correspond to either X-ray or gamma. Find out energy. Find energy like this. Students, please do copy and then solve all this. Okay. This is in EV. So these things are necessary, and electron volt concept is necessary to understand this chapter. Types of electron emission. Photoelectron emission, also called photoelectric emission, field emission, thermionic emission, and secondary emission. First one, photoelectric effect. Name itself says emission of electrons due to photons. We know that photon is a packet of energy, and if that energy is sufficient to remove electron, then that process of removal of electrons due to photons is called photoelectric effect. Let this be a metal. Why metal means there are conduction electrons. These conduction electrons are also called free electrons, isn't it? Conduction electrons or free electrons, because I am talking about metals. If this is radiation of suitable energy falls on this metal surface, then if this energy is sufficient, it can remove electron from the metal surface. So this is the electron. If this photon interacts with this electron and energy of this photon is sufficient to remove, then electron will become free. This is the standard used. To represent photon, you have to use this wave-like. To represent particle motion, use an arrow. Okay. Arrowhead represents direction of motion. This doesn't mean that photon is traveling like this. This is just a representation. Now, electron is removed due to photons. This effect is called photoelectric effect. And in this chapter, we are going to study this in detail. And photoelectric effect is observed in photocell or photoelectric cell. Just example is sufficient. Second, field emission. This is electric field. Electric field, denoted by E, is an accelerating field. magnetic field is a deflecting field. So magnetic field can divert the charged particles, whereas electric field can accelerate. Can accelerate charged particles means this electric field can supply energy to the particle, only charged particle. Now let us understand field emission. Let this be a metal plate, second metal plate. These two metal plates are connected to suitable source. Let this be plus and this terminal minus. This is a metal plate. In between these two plates which are connected to battery, there are conduction electrons or free electrons. Because of positive and negative, there is electric field, and you know direction of electric field is from positive to negative. So this is the direction of electric field. You also know that electric field is not present inside the metal. Net electric field inside the metal is 0. So this is how electric field looks like between the plates and in the presence of this metal. So conduction electrons will experience force due to this electric field. So more and more electrons will come and settle on this side because electrons are attracted towards positive plate. If voltage is increased, potential difference is increased, then electric field between the plates is also increased, then force on the conduction electron also increases. If voltage is further increased, then electric field strength also increases. Then this electric field can remove electrons from the surface of metal. Because of very strong electric field, if this electron can come out means the electron starts moving towards this positive plate. See, there is emission of electron due to electric field. So this type is called field emission. And field emission is observed in spark plug. Spark plugs are used in automobile industry, in vehicles. Spark plug. So what is field emission means? It is the emission of electrons from the metal surface due to suitable electric field. What is photoelectric effect means? It is the emission of electrons from the metal surface when radiation of suitable energy incident on it. Third type, thermionic emission. Thermionic emission. Using heat energy, electrons are removed. This is a metal. This metal is heated. Heating is represented by this symbol. If this metal is heated and the heat energy is sufficient to remove electrons, then electrons, conduction electrons present in the metal will gain sufficient kinetic energy and few electrons may manage to escape. One more electron can come out. One more electron can come out. So there is emission of electrons due to heating. Always remember, photoelectric effect, field emission, thermionic emission, all these things should be carried out in vacuum. Vacuum means low pressure. Vacuum means low pressure. Okay. Thermionic emission is observed in electron gun. electron gun, a suitable filament is connected to a battery, and this battery will heat this filament. After heating, electrons are emitted from the filament. So these electrons can be caught and used only when everything is enclosed in a chamber where low pressure is maintained. If it is done outside atmosphere, then these electrons are immediately captured by gaseous molecules present in the atmosphere. Secondary emission. In this type of electron emission, electrons are used to remove electrons. These are high energy electrons. These are made to fall on the metal surface. Then if they interact with other electrons, there is emission of electrons. This electron could be this, and this is additional electron. So using electrons are removed. So this is called secondary emission. Secondary emission, using electrons are removed. Okay. An example for this type of emission: photomultiplier tube. In nuclear physics, this photomultiplier tube is used. So using electrons are removed, or using electrons are removed. Few observations related to photoelectric effect. These are early observations. That time there was no concept of photoelectric effect. So whatever they observed, they just reported. So let us go through few such observations, very fascinating observations. Under that, first is Hertz observation. Hertz was doing some experiment. Okay. Don't worry about details of that experiment. This much is enough. He was trying to prove or disprove the existence of electromagnetic radiation as proposed by Maxwell. So in his experimental setup, he used two spheres which were maintained at high potential difference, plus minus, and a detector ring. Detector ring, something like this. Because of high potential difference, this is only for explanation. Students, please understand, this is only for explanation. If you can't follow, at least try to follow what is given. Okay. If very high potential difference is maintained, then the electric field between these two spheres could break insulating property of air. Air is a bad conductor. It is an insulator. But this high potential difference could break the insulating property of air, means it becomes plasma. That time electrons could jump from this sphere to this sphere. So these are the sparks observed between these two spheres. Strangely, in his experiment, he observed sparks between these two spheres. Understand? There is no electrical contact between these two arrangements. This is detector ring. When sparks are observed between the spheres, emitter and the collector, sparks are also observed in the detector. Why sparks are observed means, according to electromagnetic theory, light has periodically varying electric and magnetic fields. Periodically varying, let me represent it by this wave nature. So there is variation of magnetic field. Students, you have studied about Faraday's laws, right? Faraday's laws of electromagnetic induction. The varying magnetic field induces EMF. This concept you have read. If the light has periodically varying electric and magnetic fields, then that light can induce plus and minus, can induce potential difference. Because of that potential difference, electrons could jump from one sphere to another sphere in the detector ring. This was his experiment, and he successfully explained the presence of electromagnetic waves, or the nature of electromagnetic waves, or he successfully proved electromagnetic theory, or he proved electromagnetic nature of light. All are one and the same. So after doing this experiment, he did additional experiment. He made ultraviolet light to fall on this arrangement. As soon as ultraviolet light fell on this emitter plate, he could see intense spark in the detector ring. This was strange, right? Because of ultraviolet falling on this sphere, he could see intense sparks in the detector ring. There is no connection between these two. Still he could see. He reported that when emitter plate was irradiated with ultraviolet, more intense sparks were observed. Students, since you know some of the concepts of photoelectric effect, which you have studied in 11th standard, ultraviolet radiation is high energy compared to visible, and these photons are sufficient to remove electrons. If electrons are removed means, along with earlier jumping electrons, few more electrons could jump. If few more electrons could jump means, more intense electromagnetic radiation is emitted. This more intense electromagnetic radiation could induce higher potential difference between these two. That is why here also more electrons could jump from one sphere to another sphere. It's a chain reaction like. In the absence of ultraviolet, there were electrons jumping from one sphere to another sphere. Because of ultraviolet, more electrons could jump. That emitted more light. That induced more EMF. That could produce high intensity sparks. And this is Hertz observation. Observe. During electromagnetic wave experiment, Hertz observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. What's the reason for this observation? When ultraviolet radiation falls on the emitter, electrons were emitted. These emitted electrons jumped from one terminal to another terminal, which increased intensity of sparks. So these statements are enough. Lenard observation. So in Lenard observation, Lenard was doing experiments using cathode ray tubes. Evacuated tubes means suitable gas at very low pressure, These two are two metal plates called electrodes, and these two metal plates were connected to some arrangement. Let us show that arrangement by this meter. Two metal plates separated by some gas. This is evacuated glass tube. There is no deflection in the meter, means there is no current in the circuit. So this was early experiments related to cathode ray tubes. This was early experiment, one of the early experiments of cathode ray tube. When Leonard illuminated one of the plates with ultraviolet radiation, he could see deflection in the meter. There is deflection in the meter means there is current. We can't see current. We can't see electrons. But looking at the deflection, one should understand that something is reaching this plate, thereby something is flowing through the external circuit. As long as UV is incident on the plate, emitter plate, there was deflection. And if this light is cut off, deflection becomes zero. There is light, deflection. There is no light, no deflection. So this was reported by Leonard. Even diagram is not necessary. Leonard observed that when ultraviolet radiations were allowed to fall on the emitter plate of an evacuated glass tube enclosing two electrodes, current flows in the circuit as long as radiation lasts. Means as long as there is radiation, there is deflection. And what is the reason for this observation? When ultraviolet radiation falls on the emitter plate, radiation energy is sufficient to remove electrons from its surface. These photoelectrons move towards collector plate, which constitutes current in the external circuit. Reason, now you know the reason. But that time they didn't have the concept of electron emission, so they just reported this. Hall wash observation. In this first observation, this is an electroscope, glass jar, cork to seal the jar, this is a conductor, hook, this is metal sphere, C stands for conductor, metal, this is also metal, C, and this is gold foil or metal foil, thin metal sheet. If it is hung on this hook, it looks like letter, inverted letter V or U, and to this electroscope a zinc plate is attached. Let this be zinc. Metal, 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 this is also metal. If this electroscope is already negatively charged means every part will be negatively charged, this is also negatively charged, so because of negative repulsion, the gold leaf will spread out, something like this. This is the leaf, neutral. If this leaf is charged negatively or positively, then if it takes positive or negative, see, positive repulsion or negative repulsion. Because of that, the leaf will spread out, because this part experiences force, this part also experiences force due to either negative or positive charge. Angle between the ends increases means it's due to repulsion. If the electroscope is already negatively charged and ultraviolet radiation is incident on the zinc plate, this electroscope became neutral. What do you mean by it became neutral? If it becomes neutral, then these two will collapse. It will come down to this shape. Students, you can explain this, right? If ultraviolet radiation falls, then this energy is sufficient to remove electrons. Electrons are removed means this becomes neutral. Now, second observation. Electroscope, metal, this is the foil, and zinc plate. This is a neutral electroscope. Neutral electroscope means there is no force of repulsion on these two ends, therefore angle will be less, something like this. If ultraviolet radiation is incident on this, he observed charging of the electroscope. It became positively charged. You know the reason, isn't it? If ultraviolet falls on the metal, this light can remove electrons. If electrons are removed, then this zinc plate takes positive charge. If it is positive, this also takes positive charge. Positive, this rod also takes positive charge. Either side of the metal leaf or metal foil also takes positive charge. Because of positive, they will spread out like this. Now you can guess third case, isn't it? Same electroscope, cork, insulator, this is metal rod, metal sphere, this is zinc plate. If the zinc plate is positively charged, then the metal foil will spread out because of positive repulsion. Now this is the initial stage. If ultraviolet radiation is incident on this, then this angle further increased. Earlier metal foil was looking this, means it is already charged. Now it could spread out more, means because of more charge, repulsion also increases. Because of that higher repulsive force, this angle further increases. Now guess the reason. Just like above two cases, this ultraviolet light is sufficient to remove electrons. If electrons are removed, few more electrons are removed, then it takes more positive charge, more positive means positive charge on the metal plate also, metal foil also increases, therefore angle increases, which indicates that more charge is induced. First case, electroscope was negatively charged. Because of ultraviolet radiation, it became uncharged. Second case, electroscope was neutral. Because of ultraviolet radiation, it became positively charged. Third case, electroscope was positively charged. Because of ultraviolet, it became more positive. Now go through hall wash observation. Now go through Hallwash observation. A negatively charged zinc plate was connected to an electroscope. When ultraviolet radiation was incident on it, it became uncharged. Second, an uncharged zinc plate was connected to an electroscope. When ultraviolet radiation was incident on it, it became positively charged. Third case, a positively charged zinc plate was connected to an electroscope. When ultraviolet radiation was incident on it, its positive charge further increased. Important terms in photoelectric effect. Threshold frequency. For a given photosensitive material, there is a certain frequency called threshold frequency. If the frequency of incident radiation is below threshold frequency, there is no photoelectric effect. Observe metal, incident radiation. Let minimum energy required to remove conduction electrons be 2 electron volt. If energy of incident photon is 1 eV, then this is not sufficient to remove electron because minimum energy required is 2 eV. Increase energy of incident to 1.7 eV. Again, 1.7 is less than 2. Therefore, this energy is not sufficient to remove electron. Increase this energy to 2 eV. See, minimum energy required is 2 eV. Supplied is also 2 eV. Therefore, this supplied energy is sufficient to remove electron. And frequency corresponding to this energy is represented by nu naught, called threshold frequency. Observe, nu less than nu naught. Nu is frequency of incident radiation. If frequency of incident is less than threshold frequency, then there is no emission. Energy not sufficient to remove. Energy equal to h nu. Energy is proportional to nu. If frequency is less means energy of incident photon is also less. That is the meaning of this. If frequency is just equal to threshold frequency, prescribed wanted frequency for the given material, then there is emission of electrons. But we find it difficult to catch those electrons. You will understand why. If frequency of incident radiation is greater than threshold frequency, then certainly there is emission of electrons. Frequency less means not sufficient. Equal to means just sufficient. We try to avoid this case because we won't be able to find electrons. Frequency greater than threshold means certainly there is emission of photoelectrons. Again, go through this statement and copy. Threshold wavelength. First, go through this statement. For a given photosensitive material, there is a certain wavelength called threshold wavelength. If wavelength of incident radiation is above threshold wavelength, there is no emission of photoelectrons. So threshold wavelength, denoted by lambda naught, is equivalent of threshold frequency. How to get threshold wavelength from threshold frequency means lambda equal to c by nu. We have discussed this equation in the beginning of the chapter. If this is threshold frequency, then this is threshold wavelength. energy equal to hc by lambda. Energy is proportional to 1 by lambda. Lambda decreases means energy increases. Just like this, understand for threshold wavelength. If wavelength of incident radiation is less than threshold wavelength, wavelength is less means energy is more, then there is emission. If wavelength of incident radiation equal to threshold wavelength, there is emission but difficulty in finding those electrons. If wavelength is greater than threshold wavelength, wavelength greater means energy is less, not sufficient to remove electrons. Therefore, no emission. Again, go through this statement and compare these three. Work function. Denoted by phi or W. Work function is the minimum energy required to remove electrons. This is metal. Minimum energy required to remove electrons is 2 eV, means this minimum energy is called work function. So work function can be expressed in eV or in joule. If it is in joule, 2 into 1.6 10 power minus 19, which is equal to 3.2 10 power minus 19 joule. 2 eV is equivalent to 3.2 10 power minus 19 joule.